Let's jump right into this explainer and uncover the hidden exam clues you absolutely need to conquer those data verification checksum questions in your Cambridge 9618 exams. I want you to literally picture a real Cambridge computer science past paper question sitting right in front of you. Let's say it's code 9713. The timer's ticking down. The pressure is completely on. Now, typically, we see two types of students tackle this exact scenario. First, we have Alex. Alex panics, right? And just completely overloads the page with raw computer science facts about checksums, just vomiting data with absolutely zero analytical depth. It's basically a brain dump. Then, on the other hand, we have Sam. Sam rushes the question entirely, completely misses the specific command word requirements, and ends up answering a question the examiner never actually asked in the first place. And what happens? Both of these students end up with papers covered in red pen marks. Today, we're going to fix that. We are going to treat your exam like an archaeological dig. We're going to move layer by layer, unearthing the hidden clues in the question itself to reveal the perfect answer. Now, what's really, truly interesting about this principal examiner alert you're seeing is that it completely flips how we should approach complex exam calculations. I mean, this quote is a massive paradigm shift. Most students out there think computer science is just a binary game. You either get the exact right final checksum value or you get 0 marks, period. But honestly, that is a total myth. The examiners are practically begging you to show you're working. When you leave a clear trail of your logic, you unlock what we call method marks. And let me tell you, this single piece of advice is literally the difference between just scraping by with a passing grade and securing a top-tier standout result. It takes a high-stress calculation and transforms it into a structured opportunity to prove your analytical process. So, to get you those top marks, here's our map for today's dig. We're going to cover core principles, technical methodology, critical analysis, top examiner warnings, and finally, the method mark strategy. Section 1. Core principles. Let's start right at the surface layer, understanding exactly what the Cambridge syllabus demands from top-tier students when it comes to data verification during data transfer. The difference between these two approaches brilliantly illustrates why an average student like Alex falls short and a top student actually builds analytical depth. The flawed strategy is just writing down something like, checksums find transmission errors by adding up bytes. I mean, that is just super superficial. The Cambridge benchmark demands that you use structured frameworks. Think about the Peel framework: point, evidence, explanation, link. You don't just state what a checksum is, you have to explain the exact causal relationship of how the modulo arithmetic isolates corrupted data packets during network transmission, and then you link it directly back to the scenario provided in the prompt. You actually have to look at the command words in the specific computer science assessment objectives. Those red pen marks transform into green check marks the very second you stop just listing facts and start linking concepts together. To achieve those higher grade boundaries, you've got to prove you can take these core checksum principles and adapt them to completely unfamiliar scenarios. The examiners are specifically assessing your ability to master precise definitions, like, knowing the exact difference between a checksum and a parity check. They want to see you prove causal relationships, like if byte 4 is flipped, how exactly does the ones complement arithmetic catch it? And most importantly, whether you're dealing with syllabus code 0417, 0478, 0983, 0984, 2210, or 9618, you have to transfer these concepts to whatever weird and wonderful real-world context the examiner decides to throw at you. It's the ultimate trap, isn't it? Why does a concept that makes perfect sense in a textbook suddenly look absolutely terrifying on an actual exam paper? We're going to unearth the answer in just a second. But before we continue, subscribe to our YouTube channel AC Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to it. Section 2, Technical Methodology. The crucial point to overcoming that difficulty we just talked about is utilizing a strict procedural framework to decode the problem. You need a system. By following this standardized 5-step sequence, you literally stop relying on rote memorization and you start engineering your answers. This right here is your computer science success blueprint. First up, decode the command words. Are they asking you to evaluate, calculate, or describe? It matters. Then identify the key elements of the data block. Next, apply the modulo or addition principles. Step 4, execute your binary arithmetic with a perfectly clear paper trail. And finally, verify your final checksum byte and present it exactly how the prompt requested. Taking a breath and executing this exact sequence completely neutralizes the panic of an unfamiliar context. It's like having a cheat code. Let's see how this procedural framework actually builds your algorithmic thinking. This ensures you have the exact toolkit you need to tackle complex programming requirements. When a question asks you to write pseudocode for a checksum generator, you can't just guess your way through it.
You have to decompose the problem. First, isolate the loop that iterates through the data array. Then, you need to select the appropriate data structure, which is usually a 1D array of integers or bytes. You write the implementation efficiently, and then, this is huge, you mentally run a dry trace. That rigorous testing phase is absolutely crucial to ensure your logic actually catches an injected error.
A massive part of this methodology involves sharp data interpretation skills, specifically pulling evidence straight from binary representations. Let's do a quick data scan challenge right now. Imagine we've put a 60-second timer on the clock. Picture a complex data table showing a block of 8-bit binary numbers. If you just glance at it, it's just noise, right? But a top student immediately scans for the pattern, adding the binary values together, handling the carry bits, and calculating the final checksum value to append to the block. Your ability to extract that core trend from a visual sea of ones and zeros under time pressure is exactly what scores the highest marks. Moving on to Section 3, Critical Analysis and Evaluation. Once you've implemented your solution, the next layer of the dig requires you to act like an examiner, evaluating algorithm quality. Let's analyze it. Now, before we break down this table, I need you to stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, looking at this evaluation matrix, it maps out exactly what is expected when you're asked to provide critical analysis of your checksum algorithm. If the command word is evaluate, a simple description just won't cut it. You need to analyze the time complexity, like how much longer does the checksum take to compute if the data payload doubles in size. You need to look at space complexity. Does your algorithm require duplicating the entire array in memory? And crucially, edge cases. What happens if every single bit in the transmission is a 0? Testing these boundary conditions is literally what separates an A from an A star. As a quick detour here, encoding your systematic processes into a visual story is a highly effective way to trigger these steps during high-stress exams. If you totally blank out on how a checksum works, just picture a postman. The postman has a bag of 5 letters. Before he leaves, he writes the number 5 on a master clipboard. That's generating the checksum. He travels across a dangerous bridge. That's the network transfer. When he arrives, the receiver carefully counts the letters. If there are only 4, but the clipboard says 5, the data is corrupted and a resend is requested. Visualizing this simple story instantly unlocks the technical steps in your brain when you're freezing up. When comparing checksum to other methods like parity checks or ARQ, please don't just list facts side by side. You absolutely must use comparative connectives to weave your evidence together. Remember our student Alex from the beginning? Alex writes, checksums add bytes, parity checks count ones. Honestly, that's 0 marks for comparison. You need to say something like, whereas a parity check can only identify an odd number of flipped bits in a single byte, a checksum provides a more robust verification across an entire block of data, although neither method can pinpoint the exact location of the error. Do you see how words like whereas and although instantly elevate the analytical depth? It's a total game changer. Section 4, Top Examiner Warnings. Now we reach the most critical part of our dig, uncovering the top 3 traps straight from the principal examiner reports. These are the exact pitfalls costing students their target grades across all Cambridge computer science syllabus variants. Thousands of students lose marks simply because their answers are generic. Examiners want context-specific, technically precise details. Trap number 1, saying it checks for errors instead of it verifies data integrity by comparing a calculated transmitted value against a recalculated received value. See the difference? Trap number 2, forgetting that a checksum cannot detect transposition errors if the swapped bytes have the same numerical sum. And trap number 3, ignoring the scenario entirely. If the question is about a bank transferring financial records, your answer must reference financial records, not just generic data packets. Let's do a quick find the flaw challenge right here. Look at this statement. The system uses a checksum to ensure the data is safe during transfer. What is the flaw there? I'll give you a second to think about it. Got it? If you spotted that the word safe is the totally wrong terminology, you hit the nail on the head. Checksums do not keep data safe from hackers. They do not encrypt anything. They only check for data integrity and transmission errors. If you're just vomiting facts without tying them back to the specific problem and using vague, everyday words like safe, you are leaving guaranteed marks on the table. Section 5, the method mark strategy. Let's finally unearth our ultimate strategy, how to safeguard your grade even when your final calculations go completely wrong. Method marks aren't just some consolation prize. They are a reassuring, strategic safety net that rewards you for showing the exact procedural steps we just covered. Imagine you're doing a really complex modulo 256 calculation under extreme time pressure. You accidentally carry a 1 incorrectly in the second step. It happens to the best of us. Because of that, your final 8-bit checksum value is totally wrong. Now, if you just wrote down the final answer, you get 0 out of 4 marks. Ouch. But if you documented your process, the examiner sees your logic is sound, spots the minor arithmetic error, and awards you 3 out of 4 marks. You literally just saved your grade boundary by showing your work. If you explicitly show your working using these steps, examiners can trace your logic and award you marks. We call this speed writing. In the exam, you have roughly 1 minute per mark. So if we put 30 seconds on the clock right now to write a perfect paragraph, you'd spend the first few seconds writing the core formula, then you spend the next chunk of time showing the literal binary addition or extraction, and leave the final 15 seconds to clearly label your answer. It is a completely foolproof paper trail. The examiner doesn't have to guess what you were thinking, it's laid out right there on the page.
Mastering this blueprint transforms your approach from nervously guessing to confidently engineering the perfect response, layer by layer. This is the final system that guarantees top marks. First, command word decoding ensures you know exactly what's being asked. Second, applying the Peel framework gives you contextual depth. Third, following the algorithmic process gives you rock-solid structure. And finally, transparent working, our time management matrix, guarantees your method marks. This is exactly how you take an answer from 0% mark potential all the way to 100%.
When you start looking for the hidden clues within the checksum question itself, the exam becomes a simple exercise in connecting the dots. It is not just a memory test. Now, listen closely. Students who implement these computer science strategies see an average improvement of 2 whole grade boundaries. But that's only if they practice consistently with our weekly videos. So here is your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by.
I want to hear from you. Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team actually responds to every single comment. Like and share this explainer with a study partner who needs to hear this. Ace the Exams. Your Cambridge success starts here. Remember, keep your working transparent and ask yourself this. If a single flipped bit can corrupt a whole data packet, what is a single flawed study habit doing to your final grade? Keep digging, keep studying, and I will see you in the next explainer.